Today we're going to take a look at Chapter 9 in your textbook, Chemical Quantities. And basically what we're going to do in this chapter is learn how to use a balanced equation and given information to determine what the actual outcome will be from a reaction. Say we put in so many grams of a reactant, we want to know how many grams of product we get out. And that's our main focus today, using our balanced equations. By any other name, that's called stoichiometry. Okay, let's see, here we go. All right, so there are just a few sections, but each one takes a little time to get through. So don't let the short list fool you. Okay, we know that when we have a balanced equation, there's certain information that that equation gives us. It's a description of the reaction itself. Reactants go in, products come out, and we're also given information with the coefficients of our balanced equations. Tell us how many numbers of things go in and numbers come out. With the balanced equation, this can be interpreted as either the numbers of molecules that go in, or if it's an element, the number of atoms that go in and the number of molecules and atoms that come out the other side. So here's a balanced equation that I'm pretty sure is ethanol. And this is going to be a combustion reaction. I'm going to burn it. And it produces carbon dioxide and water if the reaction goes to completion. Okay, we can account for all the atoms that go in, all the atoms that come out, and that satisfies the law of conservation of mass. And we can look at it as one molecule of ethanol. Remember, we don't put ones in front as coefficients, because if it's there, there's at least one of them. So that would be redundant. So there's one molecule of ethanol. It reacts with 3 molecules of diatomic oxygen and produces 2 molecules of carbon dioxide and 3 molecules of water. That's one interpretation. We also can speak of this in terms, since we're still talking in numbers, we can use a different unit of measure, the mole. We defined the mole, didn't we? I'm pretty sure we did. Chemical reaction. Composition. I think that's what we did. Yes, we did. I need to refresh my memory. So the number of moles, 1 mole is 6.022 times 10 to the 23rd things. So 1 mole of ethanol reacts with 3 moles of oxygen, diatomic oxygen, to produce 2 moles of carbon dioxide and 3 moles of water. The advantage of using moles is there's a direct conversion between moles and mass based upon the elements and the formulas. So with oxygen, the molar mass of oxygen, right, would be 2 times 16, because 16 is the molar mass for each oxygen. So we have 32 grams per mole. So we can say if we have 1 mole of oxygen, actually instead of 3, just say 1 mole instead of 3, the ratio is still the same. Well, let's keep it simple, 3 moles. So if we have 3 moles of oxygen reacting with 1 mole of ethanol, that means we have 3 times that amount, or let's see, 96 grams. Caving in on me. 96 grams of oxygen come out as a product. If we have 1 mole of this and 3 moles of oxygen, 3 moles of oxygen react with 1 mole of ethanol, then we know that we need 96 grams of oxygen to react with that 1 mole of ethanol. And we can also calculate the mass of ethanol if we have 1 mole. Right? Just 2 times 12.01, 5 times, 6 times 1.01 for the hydrogens, and a 16. Add them all together, and that'll be 1 mole of ethanol. We can give a mass, assign a mass to that. That mass of ethanol reacts with this mass of oxygen. And we can also say, if that's the case, then we have 2 moles of carbon dioxide. So we'll have 12.01 plus 32 times 2 will be the mass of carbon dioxide. So we can assign masses based upon their mole relationships and the molar mass of each compound and element that's in the reaction. Okay, so here we have a reaction between let's see, that would be carbon 1 sulfide and carbon 1 oxide. Right? If we put names to them, which we should do for practice purposes. So this would be copper 1 sulfide. Why do I know that? Because sulfur is -2. It's a chalcogen, just like oxygen. -2, so, and we've got 2 coppers, so the coppers have to be +1 each to balance. And then we'll react with that with copper 1 oxide. Okay, and the product we're given is copper metal and sulfur dioxide. But that's not balanced. So we would have to balance it before we could do anything with it. I don't think that was going to cooperate either. Let's try this one. So how would we balance that? I'm going to leave out the phases right now. Just give me more room. All right, copper and sulfur dioxide. So our balancing method, our budget method would say we have copper, we have sulfur, we have oxygen. So on this side, we have 4 coppers, right? And we have 1 sulfur, and we have 1 oxygen. And on this side, we have 1 copper, 1 sulfur, and 2 oxygens. So typically what we do is, as one of our tricks is we hold those elements out to the last. In case there's any change elsewhere, then coefficient in front of copper will only change the copper. So let's focus on something else, say the oxygens. So if you have 2 oxygens over here, then we put a 2 here. And that would give us 2 oxygens, but it would also give us now 6 coppers, right? And we still only have 1 sulfur. So now we can put a 6 in front of this copper. And we're balanced. Okay? So now that we have a balanced equation, we can actually do some chemistry, some calculations. All right. So just to beat the dead horse further, 1 molecule of copper 1 sulfide plus 2 molecules of copper 1 oxide yields 6 atoms of copper and 1 molecule of sulfur dioxide, or 1 mole, 2 moles, 6 moles, 1 mole. Look at it either way. The more useful way is the mole way. Okay. So, oh, there was a question. How many moles of copper would be produced from 1 mole of sulfide and 2 moles of oxide? one of those, two of those, 6. How many moles of copper would we produce from 1 mole of sulfide? Oh, there are 2 questions. I'm sorry. The first question is, how many dozens of would be produced? Then how many moles of would be produced? And if this is 1 dozen, 2 dozen, that would be 6 dozen. If this is 1 mole, 2 moles, that would be 6 moles. So I think the point that's being made here is that the ratio is constant. It's always in terms of numbers. So the ratio of things is fixed. Once the equation is balanced, then the ratio is fixed. And you can say 2, 4, 12, 2, just as easily as 1, 2, 6, 1. The ratio is still the same. Okay? That's important when we start to move from one place to another in the equation, because we're going to be able to use this equation to generate conversion factors. Okay, I'll show you how that's done in just a minute. Let's see. I don't know if we need to hammer this one too hard. This is a reaction that actually I used to do in high school class. I had this device. We could put water in it. We had these tubes like that, and then the water in the bottom, and the tubes were filled, and there were electrodes in the bottom, one positive, one negative. And you had a little bit of acid in the water so it would conduct electricity, and it would produce oxygen on one side and hydrogen on the other, just like this. And you'd catch them in those tubes, and then you would demonstrate how you know it's oxygen in one side and hydrogen in the other by a glowing splint. You catch the hydrogen gas in a test tube, and you stick the glowing splint in there and it popped. It would ignite. If you put the glowing splint in the one with oxygen, it would burst into flames because oxygen supports burning of the splint. But this reaction ratio, the simplest ratio is 2:1. But 4:2 would also give you the same results. It's just not the simplest ratio. The ratio is the important point here. Okay. Now that we know the mole ratios in any balanced equation, we can say something about if we have, let's take an odd number. Let's say instead of 1 mole here, we actually have 3 moles of that compound. Okay, so we have 3 moles of copper 1 sulfide. Okay, we want to find out how many moles of copper can be produced from this. If there's plenty of that, that's not a limiting factor. If there's plenty of this, then we can convert 3 moles of this to how many moles of copper? Conversion factor to get where we're going, right? Moles of copper. We don't know yet. So we need some factor that will take moles of copper 2 sulfide, copper 1 sulfide, and give us copper, moles of copper. What's the ratio? 6 of these, 1 of those. That's the conversion factor. It's based upon the coefficients. So 3 times 6 is 18. That'll actually give us 18 moles of copper. It's like I said early on. Many problems in chemistry are dimensional analysis. They're just unit conversions. You just have to be sure that you're not violating any chemical laws or physical laws. And in this case, we just needed a conversion factor that would take us to this point, and there it is. It's the ratio of that to that. So that being said, how many conversion factors could we get out of this equation? Well, you could get 1, 2, 3, 4, 5. Going one direction. Or if you want to go back the other direction, you get 5 more. So actually you have 10 conversion factors that can be derived. I think 1, 2, 3, 4. No, excuse me, 4. You can get 4 going one direction and 4 going back the other direction. Because if you know how many of this you want, you can find out how many of that you need to get there. And the conversion factor is based upon the coefficients. Okay? I'll leave that there for a second. Okay, so here we have another example. Let's see. Sodium silicon fluoride. Actually, sodium hexafluorosilicate is the proper name for that. I thought I put it up there. Maybe I did. Yeah, there it is. Sodium hexafluorosilicate is that first compound. Why is it named this? Because hexafluorosilicate is a polyatomic ion. And it's not one that's in our list, so you don't have to memorize this one. But just for illustration purposes, that's the name it would be, sodium hexafluorosilicate. Reacted with sodium to produce silicon and sodium fluoride. Okay? So how many moles of sodium fluoride will be produced if 3.5 moles of sodium is reacted with plenty of the sodium hexafluorosilicate? So you may be wondering, why are we saying that's excess? We're going to get there. We're going to look at limiting reactants, but we're not there yet. Let's just assume for the time that we want to know how much of this will be produced from 3.5 moles of that. Okay? So where are we at? We're given 3.5 moles of sodium. Okay? And where do we want to go? We want to find out how many moles of sodium fluoride are produced. So we need a conversion factor. We need to cancel moles of sodium. I'm going to leave the moles out just for compactness. And we want sodium fluoride. Right? So this one's on top because we want to keep it. This one's on the bottom because we want to cancel it. So you look for the ratio between these two. Sodium fluoride is 6 and sodium is 4. Okay. So 6 times this number divided by that will give us the value. No?
My calculator's going back directly with the fractions again.
Oh, okay. So I'm sure I've got the answer up here. This is basically 1.5 times that. So I'm not going to trust my brain to do that on the fly. Balanced equation, what we're starting with. This is a word problem. Word problems are best analyzed if you extract the information from the problem and put it in a form that's familiar. Word problems are meant to confuse. They give information, sometimes not enough, sometimes too much. And when they give too much, I call that blue smoke. They're blowing smoke in your face. And the testing is whether or not you can pick out the information you need and answer the question. So, and I found the best way to do that is to pull out what you know. We know this. We also know that. And with this, we can get a conversion factor to give us the answer. So there's our conversion factor, the mole ratio derived from the balanced equation. That's why balancing equations is so important and why we spent time on it at the beginning. First of all, we had to learn all the symbols that we're going to be using, chemical symbols for each of the elements. Then how to write compounds and name them. So we're building. Then how to put those compounds together in a chemical equation. And then how to balance the chemical equation. So it's all feeding on itself. It's building on a foundation. And now that we have balanced equations, we're actually using them to solve real world problems. So now that we know the conversion factors, we have 5.25 moles of sodium fluoride will be produced if we react 3.5 moles of sodium with plenty of sodium hexafluorosilicate. Okay. Now, we'll say this. All of this is theoretical. Right? This is if 100% of that sodium is reacted to produce that compound. Right? And I'll just give you a heads up. In the real world, that never happens. 100% conversion never happens. There's always a fly in the ointment, but we're going to deal with it later. Okay? I'm just saying that so that you don't become enamored with this skill set and think that that's the end of it. No, there's more to it than that. Ask any chemical engineer and they'll tell you all about it. What a headache it is trying to get the highest conversion rate possible. But for now, we're going to stick with 100% theoretical, and then we'll work on the actual in subsequent slides. Okay, in this case, our problem, this is an example, an exercise. Our problem is propane fuel, C3H8, right? Same propane that you burn in your gas grill, or if your house is on the piped for propane gas, and you have a truck come by every now and then and refill it. That's the stuff that you're burning in your house. And this is the equation, the balanced equation. Isn't that nice? I've already balanced it for you. The balanced equation for the combustion of propane gas in the presence of air, which is basically the oxygen is the active reactant in that mixture, produces carbon dioxide and water in these ratios. Now, if they're balanced, these ratios are fixed. 1 mole of propane needs 5 moles of oxygen. And if it gets all the oxygen it needs, it will produce 3 moles of carbon dioxide and 4 moles of water. So the question here, the problem here is predict how many moles of carbon dioxide are formed when 3.74 moles of propane are burned with plenty of oxygen. So we would take 3.74 moles of propane, C3H8. And we need a conversion factor that will give us how much carbon dioxide will be produced. Okay. Now we need the coefficients to give us our conversion factor. Okay. One of these will produce 3 moles there. So 3 times this value will be the answer and give us how many moles of carbon dioxide are produced. Oh, I guess we're going to have to do the calculation. Let's see, 3.74 and times 3. So I get 11.22 carbon dioxide. But if we're going to obey our significant figures rules, this is a conversion factor. That's an exact number. It doesn't limit you in any way. This is the limit. 3 significant figures, multiply, divide rule. So we need 11.2 moles of carbon dioxide. Here we go. Now, we still haven't gotten to a practical application yet, because who cares about moles? Only chemists care about moles. What we really care about is, what's the mass? How much mass is produced of carbon dioxide? And actually, since this is a gas, we'd be more interested in what's the volume produced. And for that, you need other factors that are not given you. You need to know the pressure. You need to know temperature. We got the moles, and we can solve for volume. We haven't done gases yet, have we? Okay, that's fine. Consider that a teaser. We'll learn how to do that. We know how many moles of carbon dioxide. In a future chapter, we're going to learn how to convert that into a volume of carbon dioxide. But now we can easily convert it into mass. That's no problem, because we know how to calculate the molar mass of carbon dioxide and convert the moles into mass. Okay. So these are the steps that we would use to solve a problem for mass rather than moles. You need the balanced equation. That's a given. You got to write your compounds correctly. You got to balance them as reactants and products. And for most of these reactions, there are only a couple of cases where you would have to predict the products, but most of the times you're given reactants and products. Then once you have the balanced equation, you convert any masses that you're given for reactants or products into moles. The reason for that is the balanced equation is a relationship of numbers, moles, 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 moles. It's not related to mass. You can't take mass directly into an equation and spit mass out on the other side. You can't go anywhere in an equation unless you're moles. All right? And then you use the balanced equation and the mole ratio from the coefficients to convert from so many moles of this one to so many moles of that one. Whatever the case may be. Then you convert the moles back into mass. So it's a multi-step problem, but it's fairly straightforward. And we'll do some examples. I should have picked a better color. I know that green's not going to show well on the video. Okay. So we're going to do stoichiometry. That's the big word that is the umbrella word for what we're doing here. Let's see. We're eventually going to get to that topic of limiting reactants. We have the most reactants. I'll tell you what, whenever you have, let's say, a generic equation, A plus B yields C plus D. And let's say, just for argument's sake, we have 3 of these, 2 of those, and 2 of these. So we have our mole ratios here. The only way that you can go from here to there and have none of that left, it's all gone, is if you have exactly that ratio, 1 mole of A, 3 moles of B. And we learned early on in this class that every measurement if you're measuring, you're trying to measure out a mole of that, 3 moles of that, every measurement has uncertainty. So you're never going to get exactly what you think you get. One of them is going to be too much, and the other one's going to be too little. Right? That's what we call limiting reactant. In the real world, there is always a limiting reactant. You never get exactly the mole ratio that you expect. Okay. Now, for discussion purposes and theoretical, you can work your problems that way, sure. But in reality, there will always be a limiting reactant. Okay. All right. Now we're going to use those green rules that we saw a few minutes ago and work this problem. It's really simple. Synthesis reaction, element makes a compound, which means it's also oxidation reduction. So let's put this up here. I'm going to give myself some room. We have solid chromium, and we have oxygen gas, yield, Scar2O3. That's a solid. Let's see, this would be chromium-3 oxide. Okay, so we have our equation. Now we need to balance it. Right? And since we have elements here and here and over here, we can do this without the budget. This one's 2, and that one's 3. If I put that 3 over here and that 2 over here, that means 6 oxygens, 6 oxygens. Okay, now we have 4 chromiums. We just need a 4 right there. Okay, so that's the balanced equation. And it's going to show us balanced equation. There it is. 4, 3, 2. Those are the mole ratios of the reactants and products. Now what are we given? We're given 15 grams of chromium. All right. And they tell us that this is excess. So there's no limit to the oxygen. When the reaction is complete, all this chromium will be gone, and we'll have an extra oxygen around. And the question then is, how many grams of chromium-3 oxide are produced? Right? Okay, now we have the word problem on the board. We stole it away from its prison here in the word problem. And now, in order to go from here to here is where we want to go. We can't get there. Think of it like this. The great walls of stoichiometry. You can't get over those walls or under those walls with mass or any other measurement, unit of measure, except moles. You've got to have moles to go anywhere in that equation. Okay? So we take this 15 grams and we have to convert it to moles. We know how to do that, right? Grams on the bottom cancel, moles on the top. Anytime you have moles and grams in a quotient, that's molar mass. So the molar mass is chromium. So we go to our periodic table and we look up chromium. Let's see, chromium is here. 52.00 rounded off. There we go. So we divide 52 into 15. And I get, now I'm going to use my trick for avoiding rounding errors. I'm not going to round these to significant figures yet. What I'm going to do is keep all of my decimals, and as many decimals as I want, and I'll only round at the end, because all of these operations are going to be multiply divide. That's why I can do that. So this is going to be 0.288469. grams of chromium. Oh, excuse me. I just shot my whole premise in full of holes. Moles of chromium. Right? I can't go anywhere with grams. I already had grams. Now I got moles. Okay, so we got this many moles of chromium, and we want to find out how many moles of chromium 3 oxide are produced. So if we've got this value here, right, we want to go from chromium to chromium 3 oxide. Now we know that the conversion factors derived from the coefficients, there's 4 here and then 2 here. Okay, so that's a half. We just take this value and divide it by 2. 0.14423. This is moles of chromium 3 oxide. Okay, because we canceled that and left us with this one. We're not there yet. How many grams does that represent? 0.14423 moles of chromium 3 oxide. We need to convert that back to grams. Grams on top, moles on the bottom. In this case, we have grams on the bottom, moles on the top, because we wanted to end up with moles. Here we want to end up with grams. So we need the molar mass of chromium 3 oxide. Right? So we need 2 chromiums, 52. That's 104 for this. And then 3 oxygens, 3 times 16 is 48. So that's 152 grams per mole. So this is multiplied now by that. And I get 21.9231 grams chromium 3 oxide. Now we can round it to significant figures because these were all multiply, multiply, multiply. And we started off with 3, so we can round this to 21.9 grams of chromium 3 oxide. Okay, here we go. That's our first calculation. This is our second calculation. And our final gives us the mass. 21.9 grams. Okay. I could have just blasted through those slides, but that meant that the information would have just gone in one ear and out the other. If you take time and do it like this is a permanent record, of course, right on the slides. And it's more legible than my handwriting. But you can see it done step by step this way. That's why I show you both ways. All right. One thing that I didn't show you was we know how many moles of chromium are involved, how many moles that represents. We can also find out how many moles of oxygen does it actually consume. We just use that ratio, 3 to 4, and find out how much oxygen is required. Convert it to mass. We could have done that. I'll leave that up there just a second in case. Well, this is in one step, which is personal preference, whatever you want. You're just converting, right? Canceling, canceling, canceling. There's your answer. Okay. What do we have coming up? Come on. There we go. All right, another problem. Tin-2 fluoride is added to some dental products to help prevent cavities. That's how they get fluoride into your toothpaste. If you look on the tube or the box, you'll see the ingredients, and it won't say tin-2 fluoride. That's the standard notation for chemists. What they use is what we call a trivial name, which is an older form called stannous fluoride. So if you see stannous fluoride, that's what they're talking about. Okay, tin-2 fluoride is made according to the following reaction. Okay, so it looks like it's balanced. Let's see, 110, 110, two fluorines, and two hydrogens. That equation has been balanced for us. Okay, what's the question? How many grams of tin-2 fluoride can be made from 55 grams of hydrogen fluoride? This product right here, reactant, if there's plenty of tin available. Okay, what is that? Right? We named compounds before, didn't we? Starts with an H, that means it's an acid if we put it in water, and it is in water. So what would it be called? Let's see. No oxygen starts with hydro, right? And fluoride becomes ic, hydrofluoric acid. That's what that is. Now, if it's not too concentrated, it's not particularly hazardous. But if you're using concentrated hydrofluoric acid, which I have done in the past, you have to be really careful. It's not just the acidity, it's the reactivity of the fluoride. If you get some of that on your hand, it will just keep going until it comes out the other side. So it's some nasty stuff. Anyway, enough with the stories. The question is, how many grams of this product can be produced from 55 grams of that product? Right? So we need our balanced equation. And 2HF yields that product and that gas. Now we're given 55 grams of hydrogen fluoride, hydrofluoric acid. And we want to know how many grams of this can be produced. So there we have everything that we're given in the problem. And we have to see, all right, what else do we need? Well, remember, we got to convert that to moles, right? That has to be converted to moles. So we need a molar mass for HF. 1.01 plus fluorine is 19th of it. Exactly 19th. So it'd be 20.01. There we go. Divide 20.01 into 55. And I get 2.749. Moles of HF. Okay. Now we want to convert that to moles of stannous fluoride. Okay, HF here and SE. 2 there. So the ratio is 2 here and 1 there. So again, we take a half of that. And that's 1.374. Moles of SNF2. Because that cancels, that cancels. That cancels. Now we're going to convert back to grams of this one. 1.374 moles of SNF2. And we want to convert that to grams from moles. So we need a molar mass. 10 is 118.71. And then we need 2 fluorides at 19 each. Right. That's 38. So that's 156.71. There we go. Multiply that number times 1.374. Now I get 215.369. Grams of stannous fluoride. Okay, now we can round it off to 3 places. 215 grams. Okay, and there it is. Well, that's in one step. We just took all these and strung them together. And our answer is right there, 215 grams. Let's see. What's next? Okay, new equation. Okay, that's good. We're still recording. It's nice to check every now and then. Lost somebody. Martina. Let's see if there's a chat message. Maybe she said why. Nope. Okay. Consider this equation. Phosphorus trichloride, right? Type 3 compound, non-metal, we just name it. Phosphorus trichloride, that's the name. Water, dihydrogen monoxide, and phosphorus acid. PO3 is phosphite, and ites become uses in acid naming. Phosphorus acid, assuming it's in solution, and it probably is, and hydrochloric acid. What mass of water is needed to completely react with 20 grams of PCl3? Right? Let me see how we're doing on time. Coming up on 10. I think we're good. We can do this one. PCl3 plus 3 waters yields H3PO3 plus 3HCl. Okay. What mass of water is needed to completely react with 20 grams? So we got 20 grams of this, and we're looking for the mass of that. Right? So we're not going all the way to products. We just want to know how much water does it take to use up all of that. So we would convert 20 grams of this to so many moles. We just need the molar mass. Let's see, phosphorus is 30.97. 30.97. And then chlorine is 35.45 each times 3. And then add those together. 137.32. Check me out to be sure. That gets rid of grams and leaves us with moles. So divide that number into 20. And I get 0.1456. 0.1456 moles of PCl3. And then we have that we want to convert to moles of water. So we have PCl3 here and water here, and the conversion factor is one of these and 3 of those. So 3 times that value. 0.4369. 0.4369 moles of water. Okay, now we just need to convert water, moles of water back to grams. So that's moles canceled, leaves us with grams. So how much does a mole of water weigh? I haven't memorized. 2 hydrogens, 2.02, and 16 for water is 18.02. Times 0.4369. Okay, 7.874. 7.874 grams of water. Right, now we can round 3 places. 7.87 grams of water. Here we go. So what we're showing is that you can do stoichiometry across the arrow, or you can stay on the same side of the arrow. Or we could go over here. If we're given so much of this, how much of that are we going to get? It doesn't matter. As long as you've got the balanced equation and the ratios are established, then you can work the problem any way you want. Whatever you're given, where you're going, it's just a math problem at that point. Okay. Are we going to get enough? Oh, okay. Yeah, do a little detective work. Okay. I'm going to write this one on the board. So we have 6 x's, which is in the solid phase, and x is an unknown. We don't know what it is, but it is an element. We know it's an element because it's all by itself. And we're going to react that with 2 B2O3. Diboron trioxide. I think there's another name for that. And we're going to get this one, E4X3 plus 3XO2 gas. Okay. We're given this balanced equation and other information we're given, 175 grams of X, 175 grams of X reacts with diboron trioxide to produce 2.43 moles of this compound. 2.43 moles of that compound. What's X? Okay. Whenever you're asked to identify an element, ask yourself this question. What information do I need to identify the element? We know that if we have the atomic number, simple. Just go to the periodic table and run the numbers until you get to the one that's yours. There's your element. But then you ask yourself, do we have information enough here to tell us that? No, because that's the number of protons. We're not given any subatomic information here. We're given atomic, molecular information. All right. So there's another thing about the periodic table that's helpful. As you increase the atomic number, some of protons, you're also increasing the weight or the mass, the molar mass of each element as you go. And they're unique values most of the time. There's some overlap. There's some elements up there that are so close together that experimental error may cause you to wonder whether it's this one or that one, but it happens very seldom. So if you know the molar mass of the element, you can probably identify what it is based on the periodic table. So what do we need? What's molar mass? Molar mass is grams per mole. Okay? We got the grams right here. That's how many grams it is. What we need to know is how many moles does that represent? Then we can plug in the moles here and get a molar mass and go to our periodic table. Okay, so the question is, how do we find out how many moles of this there are? Well, we know how many moles are produced here, right? Can we convert that number of moles to this number of moles? Yeah. So we just say 2.43 moles of this compound, B4X3. And we want to convert it, B4X3, to X. The ratio is 1 to 6. Okay? So if we just say 6 times that number, 2.43, 14.58. 14.58 moles of X. That cancels. Now we got both values that we need. So the molar mass of this compound is 175 grams divided by 14.58 moles. So I need 175 divided by that number. And I get 12.00. 12.00 grams per mole. So now we go to the periodic table. We follow along from left to right, top to bottom. The molar masses get bigger too, just like the atomic numbers do. So we follow along from left to right, top to bottom, until we get to one that's close to this value. And what do you got? Which is carbon. Yeah. So that's X, carbon. All right. Little Sherlock Holmes there. Yeah, not really. Sherlock Holmes is more like you have 4 or 5 different possibilities. You can eliminate them until the one on the left is the logical one. Okay. Remember when I was talking earlier about reactants to products, and in order to go from all reactants to all products, no reactants left, you had to have exactly the right number of moles of each of the reactants. That's called a stoichiometric mixture. If you have a stoichiometric mixture, then theoretically you have exactly the right number of moles of reactants to each other to produce nothing but products once the reaction is completed. And like I said before, that never happens, not in real life. But it's a good starting point. So the stoichiometric mixture here would be what? 1 mole of nitrogen gas and 3 moles of hydrogen gas. If that were the case, theoretically, you would produce 2 moles of ammonia. Okay? And this is what it would look like if we could get down really small and watch the molecules move around. Right? In this mixture, you have 1 mole of nitrogen, 3 moles of hydrogen. And everybody's got their right partners. 1, 3, 1, 3, 1, 3, 1, 3, 1, 3. Produces 2 of these for that group, 2 of these for that. That's a stoichiometric mixture. But this is what really happens. For instance, if we had enough hydrogen for that nitrogen, and enough for that one, and enough for that one, but we got some extra nitrogen, right? There's not enough hydrogen for those. That nitrogen would be considered excess. That makes the hydrogen limiting. Okay, the reaction is limited by hydrogen, and And when the hydrogen runs out, the reaction stops. And you still have these unused nitrogens left over with the ammonia mixed in. That's what really happens. Okay. Come on. There we go. In other words, the limiting reactant is the one that runs out first. And that's, we're going to use that fact to determine the real amount of product that can be produced from a reaction. We have to identify which one's the limiting reactant. Okay, so we'd probably be better using a real example. Yeah, there's one kind of. Methane and water react to form products in this equation, right? And that one's balanced. 6 hydrogens, 2 plus 4 is 6, 1 carbon and 1 oxygen. Okay, so we're good there. All right, so we have this methane reacting with water to produce 3 hydrogen molecules and 1 carbon monoxide. Okay, what are we given? Well, if we have 1 methane and 1 water, here we go, methane and water, methane and water, methane and water. These two are extra. Yes, those are excess. So the water would be limiting. Now let's see. There's your 3 hydrogens, there's your carbon monoxide. It's not showing us the excess. These two, this one and this one are in excess. Well, that's another way to look at it too. The ratio of methane to water needs to be 1 to 1, right? 1, 2, 3, 4, 5. 5 to 3 is not 1 to 1. So we know that's not stoichiometric. Water's used up first, means it's limiting. Methane is left over, it's excess. And limiting. Okay, that's fairly easy to see when we're given picture structures like that. What you're usually given, though, is masses or amounts of the reactants. Then you have to figure out which one's limiting. Okay, so that takes a little bit more work. Okay, so if we're going to solve a limiting reactant problem, we do the same thing as we did before. Balanced equation, convert all masses to moles. Right? Then we use the number of moles of the reactants and products to see if the ratios are right. That's one way to do it. I've got a simpler way, an easier way. I should have changed the slide for that anyway. And then once you find out which one's limiting, then you have to use the limiting one to determine the amount of products, because the excess is going to have leftovers. So the limiting one is the one that tells you how much of the products you can actually produce. All right, so let's do an example. Oh, not A's and B's. All right, well, we'll do that. So we have a chemical A reacts with chemical B. What's the formula? We need a balanced equation. Okay. Is he going to give us one? No. So we can skip it. Let's go to a real one. This is a real equation where we have 10 grams of aluminum and 10 grams of oxygen react to produce aluminum oxide. In that balanced equation, 4 aluminums plus 3 oxygens yields 2 aluminum oxide. Okay, what are we given? 10 grams of aluminum and 10 grams of oxygen. Now, just looking at that, you can't tell which one's limiting, right? Because it's not mass-mass ratios, it's mole-moles. We're also given the molar mass of aluminum, which we will need, the molar mass of oxygen, which is wrong. O2 is 32 grams per mole. There's mark that. Yeah, oxygen, individual oxygen is 16. Okay, problems are written right. It's just this part of the problem as well. Fix that slide. Okay. So, what mass of product will be produced? So we want to know how many grams of that product are produced. The key to recognizing whether or not you have a limiting reactant problem, the first indicator, you're given absolute amounts of each of the reactants. In this case, there are 2 reactants. There could be 3 or 4 reactants. If you're given absolute amounts for at least 2 of them, you know that there's a limiting reactant in there. So we operate on the premise that one of these is going to be limiting. Oxygen or aluminum will run out first. We just need a way to figure it out. Okay. The easiest way, I think, is not to say how many moles of this and how many moles of that, and are they stoichiometric or not. Since the problem is asking us how much aluminum oxide is produced, then why don't we say, what if all of this is used up? How much of that is produced? What if all of this is used up? How much of that is produced? The one that produces the least amount is the limiting one. So we'll take this one, 10 grams, and convert it to moles of aluminum, okay, using 26.98 grams per mole. Okay, so how many moles is that? Let's see. That's 10 divided by 26.98 is 0.3706 moles of aluminum. Okay. How much aluminum oxide does that represent? Well, the ratio is 4 to 2. So if I want to cancel aluminum and leave me with aluminum oxide, this one cancels there. The ratio is 2 here and 4 there. So 1/2 of that value is 0.1853. 0.1853 moles of aluminum oxide. Now, for our purposes, that's as far as we need to go right now. Right? We just need to know how many moles can be produced from that many grams of aluminum. Now, how many moles can be produced from that many grams of oxygen? Okay, so that's 32. So 10 divided by 32 is 0.3125. 0.3125 moles of oxygen. Now we want to convert oxygen to aluminum oxide. So the ratio is 3 oxygens and 2 aluminum. So how many moles of will that be? Now let's see, 2 times this value divided by 3. 0.2083. 0.2083 moles of aluminum oxide. And now we can tell which one runs out first. The aluminum is going to be consumed first. It produces the least amount. So now that we know, so this one's out. This is the value that we're working on here. You want to convert that to mass of aluminum oxide. And it's given here as 101.96 grams per mole. So I'm going to have to erase this part. So we're going to multiply that times moles on the bottom, grams on the top, 101.96. And I get 18.895. 18.895. Is that reasonable? That's about 2/10. Yeah, that's reasonable. Grams of aluminum oxide. And then we can round off 3 places. So it's actually 18.9 grams of aluminum oxide. Okay, there's a conversion to moles of aluminum. There's a conversion to moles of oxygen, which I erased. Then you want to convert each one of those to how much of that you could produce. The other one, how much of that. So the aluminum is the limiting reactant. And then you take the output from that one and convert it to actual mass of this one. So we're going to have some excess oxygen in the reaction vessel, and all the aluminum will be consumed. Okay, any questions? Okay, let's see. All right, this is just a cautionary note. You can't simply add the total moles of all the reactants to decide which reactant mixture makes the most product. You have to always think in terms of which one's limiting in the balanced reaction. And then determine how much product can be produced. And again, this is 100%. That's if everything is converted, 100%. What you actually get from the reaction will usually be less than that. If you get more, then you know there's contamination. Okay. Which of the following reaction mixtures could produce the greatest amount of product? Each involves this reaction. Hydrogen plus oxygen yields water. Let's see, is that right? 2 is 4. That's right. Okay, we're talking in moles only here. How about 2 moles of hydrogen and 2 moles of oxygen? Let's see. We put A, B, C, D, E. All right. Produce the greatest amount of product. Okay, how much product would A produce? 2 moles of hydrogen. Oxygen is excess, right? We only need 1 mole. Right? So 2 moles of hydrogen means 2 moles of water. 2 moles of water. How about B? 2 moles of hydrogen and 3 moles of oxygen. Well, you still got excess oxygen, don't you? So it's the same amount. How about 2 moles of hydrogen and 1 mole of oxygen? What is that? Stoichiometric mixture. 2 moles. 3 moles of hydrogen and 1 mole of oxygen. Now, you got too much hydrogen. So 1 mole of oxygen produces 2 moles of water. And each produces the same amount. There is your answer. Each situation produces the same amount of product, theoretically. All right. Let's see. Do I want to mess with this? What else do we have to go? Spend time on this one. Nah, I think we're going to beat the dead horse. I want to skip this slide and go to a real world. Okay. So we're back to the Haber process. This is how he produced ammonia for the German war machine in World War I. Okay. How many grams of ammonia can be produced from the mixture of 3 grams of nitrogen? Oh, and each 3 grams of hydrogen. All right. There are choices. And there again, you got given amounts for each of the reactants. We know one of them's going to run out. So we need to find out how many moles of this nitrogen do we have first, and how many moles of the hydrogen do we have. So 3 grams of nitrogen. Nitrogen is 14.01, so N2 is 2802. 3 divided by 2802. 0.1071. 0.1071. Right? Yep. That's moles of nitrogen. Let's go ahead and find out how much ammonia would that be. Right, so we have nitrogen down here, ammonia up here, and then we need the coefficients. 1 and 2. So 2 times that would be 0.2141. 0.2141 moles of ammonia. Okay, so that's how much this would produce. How much would the hydrogen produce? 3 times 1 mole. 2 hydrogens is 2.02 grams. So 3 divided by 2.02 is 1.485 moles of hydrogen. And let's convert that to ammonia. Ammonia on top, hydrogen on the bottom. So hydrogen is 3, ammonia is 2. We need 2/3 of that number. Is 0.9901. 0.9901 moles. Okay, so that was fairly easy. We can see that the limiting reactant here is nitrogen. So we just need to convert that back to grams. 0.2141 moles of ammonia moles grams. So ammonia would be what? 14.01 and 3.03 for hydrogen, right? 3 times 1.01. 17.04 times 0.221, let's see, There we go. 3.65. Rounded off 3 places. Okay. So there are the conversions. Yeah, a lot of rounding in there. We ended up in the same place. 3.65 grams of ammonia. Because this one's limiting, this one's excess. Before I erase that, let's see what's on the next page. I'll leave it there for a second, just in case. Now we're talking about, we've gotten some idea as to what limits the reaction. Right? One of the reactants is going to run out first. And when that happens, the reaction stops. But as any competent chemical engineer will tell you, if you collect the product, ammonia in this case, at the end, after reacting 3 grams of nitrogen, you will not get 3.65 grams. You get something less than that. And there are a host of reasons for that happening. One is, maybe under those conditions of the reaction, all of that really didn't react. And that's true for the Haber process. It doesn't go all the way to completion like this. In other words, it goes like this. It can go either direction. Right? So it only goes a certain way this way before you build up enough of that to start sending it back the other direction. That's one way. That's an equilibrium problem. The other is having to do with isolation of the product. Right? When you isolate the product, you're always going to lose some. Like you can never get 100% recovery. If we did actually get 3.65 grams produced there, when you isolate it, you're going to lose some in the process. Since it's a gas, you may have a leak in your system. Or if it were a liquid or a solid, well, you could have a leak there too. Or if you had to separate a solid from a solution, right, filter it, you may not get all of it. Right? Some of it might go through your filter and stay in the effluent. So there are a whole host of different reasons that your yield is not going to be 100%. So what we need is to quantify what that yield is. Then we can use that information to do some real world calculations. And that's called percent yield. We have the theoretical yield. That's what this is. That's theoretical, 3.65 grams. That's when we've taken the limiting reactant into account. That's where we're at, the theoretical yield. The actual yield is what you actually measure as your product. And then you compare them. In fact, you just ratio them. You put the actual on top, the theoretical on the bottom, divide them and multiply them by 100, and you get percent yield. Here we go. Just like that. Simple, simple. But, as in the case of all percent values, once you have that percent number, it's dimensionless. It just means parts per 100 parts. You don't know what the parts are, unless you know where it came from. If we're identifying this value as percent yield, then you know the source of the information, and you know the values that are equal to it. So you could say actual mass divided by theoretical mass times 100 equals percent yield. With that formula, if you know two of those, you can find the third. If you know this value and you know this value, you can find that value. Or if you know this value and that value, you can find that one. Or if you know that one and which one did I do before? This one, then you can find that one. It's like any math expression. Okay, so they're throwing an A and B at us. I use those when I have to, but I don't like it. Let's get down to the last two slides. They actually use real reactions. What I ought to do is just dump those slides. Then I won't have to keep skipping them every time I do this thing. Now, there's one, I do remember one problem in the review document that is percent yield based upon moles. Now, that's valid as long as you know where it came from. So you're going to have to use moles for that one instead of mass. But it's still actual divided by theoretical times 100 is percent yield. Okay. Here we go. Find the percent yield of product if 1.5 grams of sulfur trioxide is produced from 1 gram of oxygen and excess sulfur. Okay, so let's put our equation up here. Balanced equation. And what are we getting? 1.5 grams of sulfur trioxide is produced. 1.5 grams actual. From 1 gram of oxygen. And excess sulfur? Yes, excess. Okay, so what we need to do is find out what the theoretical is. We're given the actual. So 1 gram of oxygen that would be 32 grams per mole. So 1 divided by 32 is 0.3125. Oops. No, 0.03125. It's oxygen. Then we just need to convert that to moles of sulfur trioxide. Oxygen on the bottom, sulfur trioxide on the top. We have a coefficient here of 3 and a 2 there. So 2/3 of that value is 0.02083. Moles. Moles of SO3. Now we need to convert that to mass. So sulfur is 32.07 from the periodic table. In O3, 3 times 16 is 48. So that's 80.07. Times 0.02083. And I get 1.6, how many significant? 3 significant figures. 1.67. 67 grams theoretical. So now to calculate percent yield, we just ratio those two, 1.50 actual, 1.67 100 equals what? And I get 89.9% yield. Now, rounding error, 89.8. I know what happened. I rounded it here, but I didn't round it in my calculator. And that gives us, well, now, should be 89.9. 1.5 divided by 1.67, let me do that again. Okay, I was right the first time. So that's how you do percent yield. Now, the last one is a little bit more complicated, but as always, the rule is you take a complex problem and you identify what's the question. And then, if necessary, you break the problem into smaller pieces, manageable pieces. Logically speaking, right? You don't break them into random pieces, right? You don't just throw it on the floor and watch it break. You break it up into logical steps that can then be combined to give you the answer. Okay, so here we have P4. I'm going to leave out the phases here. And 6 fluorine yields 4 PF3. See? Yeah. What mass of P4 is needed? Mass of P4. What mass of P4 is needed to produce 85 grams of PF3? 85.0 grams actual. That's what they're saying. We want to guarantee that we have 85 grams output. If we know the reaction is 64.9% efficient, that's the yield. So this is the product of theoretical times percent yield. Yields that. Well, actually, it's not percent yields. It's actually the fractional equivalent of percent. So what we need is this value would be 0.649. Did I lose anybody there? We need the fractional equivalent, or we could do it this way. 85.0 grams divided by X grams, which is the theoretical, times 100 equals 64.9. Okay, there we go. So now, if we take the 100 to the other side, divide 100 into that, we get this value. And if we want to know what X is, now we've got X equal to 85 divided by 0.649. And that's the theoretical amount of PF3. 85.649. So that's 130.97. 130.97 grams of PF3. Now we can use the equation. Okay. Did I lose anybody? This is the theoretical amount. This is the actual amount. The ratio of this one to that one is 64.9%. We just work backwards. We work backwards through the formula to find out what the theoretical amount is. Because you can't go from actual to here. If you do, if we did it from here, moles, grams here, then when you actually did the reaction, you'd end up with 0.649 times that value, and less than you predicted. So we need to to have this theoretical amount, go back here and say, how much of that do you need in order to guarantee 85 grams actually? So that's why we need this value. Then we convert this to moles. PF3. Phosphorus is 30.97. And 3 fluorines, which is 19 each, times 3. Add those together. 87.97. Okay, divide this into this. Okay, and I get 1.489. 1.489 moles of PF3. Then we convert that to moles here. So we need to get rid of PF3 and leave us with P4. Coefficient there is 1, coefficient here is 4. So we just take a fourth of that value. 0.3722. 0.3722 moles of P4. Now we can convert that to mass. But don't forget, this is P4. So we got to take phosphorus at 30.97 times 4. That's 123.88. 123.88 times 0.3722. And I get 46.1. 46.1 grams of P4. That's how much P4 we need to guarantee a production of 85 grams of the product at 64.9% yield. Okay, there are the steps in black and white. There we go, 46.1 grams. Okay. I think that's the last slide. Yep. Okay. So the review document will give you some practice doing these. And as usual, chemistry builds on its past. You got to master what you know now in order to go ahead with the future. And we're 20 minutes early. Okay, any questions, comments, complaints, problems? Okay. These documents, well, you saw the slides. This is the Chapter 9 review document. Let's see, move it over here like that. Oops. Okay. Looks similar to all the rest. And here's the Chapter 9 work problems. Okay. You'll find those in Brightspace. And there's a key for the review that I didn't print out this time. And then, what is today? Tuesday? Thursday, we'll do a review. And then you'll have till the following Tuesday to do the exam on this. And so, as usual, you don't have to show up for the exam unless you're going to come in person. I'll be Zooming anyway at the beginning in case you have any questions that we need to iron out before you actually start the exam. Or if you're trying to do it and something glitches, then you can Zoom into me and tell me what your problem is. And if I can't fix it, I'll pass the buck to IT. Okay? All righty, we're done for today.